Okay, you should have out lecture 37, central limit theorem examples. And I say here, recall the central limit theorem, which is this amazing mathematical fact about the entire universe. And I say it's a mathematical fact because it is not a fact we arrive at by gathering data and analyzing the data. It is a fact about the way data behaves, and it's entirely mathematical, and it's true across the universe. It's really amazing. And what is it? It's that if you have a population of data with a mean of mu and a standard deviation is sigma, however that data may be distributed, normally or uniformly or in some other crazy way, if n is large enough, and for our purposes n bigger than or equal to 30 suffices, we can take samples of size n, and that yields a new population of data, the population of sample means for that size of sample, and the result is that population is normally distributed with mean mu and standard deviation sigma over the square root of n. And I have all that written there. So what we end up with is, actually, I don't think I'm going to write it because I've got a lot to write and I don't want to crowd things. We end up with that sample mean being normal, mean, the original mean, and standard deviation, the original one divided by the square root of n. But the important thing is it's normal with that bell-shaped curve. And I make the observation, again, that the criterion that n has to be big enough, bigger than or equal to 30, we can throw that out the window if we happen to know that the original population of data is normally distributed. In that case, it doesn't matter how small the sample size is, the sample mean will also be normally distributed. All right, I've got just several examples here, I guess. So I just want to get right to them. So, first example here. After extensive testing, Rolling Tires has concluded that its basic tire has a mean life of 60,000 miles with a standard deviation of 4,000 miles. So, question one. I will write minimally here just so we can save time. If we picked 4 of these tires at random, what is the probability that the mean life of this sample is less than 58,000 miles? All right, we always need to kind of start with defining a random variable, which is our way of saying how do we reach in and pick out a random data point from the population of data. We got to call that something. So let's say let t equal the length of life in miles, of course, of a randomly chosen tire. All right. With the sample size n equal 4, what we want is then, so let's read it. What is the probability that the mean of this sample of size 4 will be less than 58,000 miles? So we want the probability that t is our random variable, arbitrary data value. So we want the probability that t bar, the sample mean, is less than 58,000 miles, right? That's what we're asked for. And the whole point of getting all this up here is then to say, well, we can't do it. We can't do it. And why can't we do it? We are not told that the original data is normally distributed. Therefore, in order for us to be able to do it where we could find z-scores and use the z-table, we'd have to know that the sample mean were normally distributed, and the sample size is too small, n equal 4. So we can't conclude that with such a small sample size, things have smoothed out to give us a nice bell curve, right? We don't know that the original data has a bell curve to it. So we can't do it because n is too small. N equals 4, which is less than 30, and don't know if the original data, we don't know if t is normal. Just say it like that. If we knew that, we could proceed. But we can't. So, and once again, I will say, look, we can go through and do the problem. We can compute z-scores here. We can subtract the mean and divide by the standard deviation all the way across, and we can get an answer. The point is we just don't know if we can believe that answer. We can't really trust it because we're assuming normality in order to assume that when we get the z-score, we have a nice z random variable. We might not, where we would use the table, but we might not, so it could be invalid. Next question, though. Same question, but n equal 36. Well, okay, obviously 36 bigger than or equal to 30. So we can use the central limit theorem and say that T bar is normally distributed with the same mean, and I haven't written up here, but it's 14,000, right? And standard deviation is the given standard deviation, which is 1,200 divided by, I have those numbers right, don't I? No, you know what? I'm mixing it up with another problem. All right, problem we're coming to, my mistake. The mean is 60,000, that's better. And the standard deviation was 4,000, but for this sample of size 36, we divide by the square root of 36 to get that standard deviation. So we get normal 60,000, and 4,000 divided by, that'll be by 6. We end up with 666.6 repeating. Okay, so there is the probability distribution of T bar. So what we want is the probability that T bar is less than 58,000, right, miles. So we do our conversion, and of course you've stopped me and done this already. We convert now, because we have the normal curve on T bar, we can convert to z-score and know that we can use the z random variable. So I subtract the mean, which is 60,000, divided by this standard deviation. And you might be tempted to round. I'd rather not round right now. We'll round soon enough, but I don't think we'll need to, because what will happen is then we have 58,000 minus 60,000 divided by 666.6, and that becomes, let's see, I think I have room right here. Do I? Yeah, this is good. So that's the probability that becomes z, great, and this becomes negative 2,000 divided by, negative 2,000 divided by 666.6666, and it becomes out to be exactly negative 3. All right. And if we look that up, we will get, most tables will give it as about that value, 0.001. All right, so it's a 1 in 1,000 chance that if we grab 36 of these tires and we measure how long the length of life of each one is in terms of miles, and we compute the mean, it's a 1 in 1,000 chance that mean will actually be less than 58,000 miles, if in fact it is true that the original mean was 60,000 miles, right? Okay, so that's that one. And let's see, let me jump to the next one, which will maybe change color here so it'll be a little easier to see. Okay, the next one says, now we're on to this, the length of life of a basic light bulb from the Bright Idea Light Company is normally distributed with mean 14,000 and standard deviation 1,200. This is the one I started to do in the middle of doing this down here. Okay, so let's let L equal lifetime hours of a randomly chosen bulb. I always need to define my random variable, which again is like a random data value from the original data set, because I'm going to then look at sample means, so I'm going to use, I need to have that symbol with a bar over it, right, for the sample mean, so I know what I'm talking about. Okay, we're given from the start not just that the mean is 14,000 hours and the standard deviation is 1,200, but we're given that it's normally distributed with mean 14,000 and standard deviation 1,200. All right, so number one says, what's the probability that a bulb chosen at random will have a length of time greater than 15,000 hours? So I want the probability of just a bulb chosen at random being greater than 15,000. So, up here I say let L equal lifetime hours. I mean of a randomly chosen bulb, right? Of a randomly chosen bulb. Okay, that's always understood that we're choosing randomly. I just didn't say it there explicitly. Okay, well, we can proceed because we know that L is normally distributed. So it's like we're taking a sample of size 1, right? We're letting n equal 1, which is a lot less than 30, but of course that's okay because the original data here is normally distributed. So I got L greater than 15,000. By now, you should have the answer, right? You should have me paused and have the answer. But let me just run through it. So it's probability that L minus 14,000 divided by 1,200 is greater than 15,000 minus 14,000 over 1,200. And this works out to be the probability that becomes Z, and this becomes 1,000 over 1,200, which is 5/6, or 0.833333, right? So I'll just write it as 5/6. So that is 1 minus the probability that Z will be less than 5/6, and that's 1 minus 0.7967, I think, 7967, so that's 0.2033. Okay, so a little over 20% chance that a bulb chosen at random will live to be more than 15,000 hours old, all right? Let's go to, what color? Maybe blue. All right, let's go to, let's see if we pick a random sample of size 4. So let n equal 4. All right, in this case, L bar now will be normally distributed with the same mean, 14,000. And the standard deviation will be the old standard deviation divided by the square root of the sample size. So it becomes normally distributed with mean 14,000 and standard deviation is 600. All right. Well, you work through the details, and if what we want here, we want the probability that L bar is greater than 15,000 this time, right? And you work through the details. You should already have it done. And before we even do it, let's think for a second. Isn't it true that if I have 14,000 here on the number line, that's my mean, I'm looking at 15,000, which is a little bigger, all right? So the tail probability associated with 15,000 for a randomly drawn bulb is a little over 20%. But now, because I'm looking at a sample mean, I know the probability gets tucked in, gets pulled in a little closer, so I expect the probability in that tail to be smaller. And in fact, it is. It turns out to be 0.0475. All right? Or not finally, but number 3. And what's the probability of sample size? 36 has a mean life greater than 15,000. So this time, n equals 36, correct? What is the new sigma? Well, pause me and figure it out, and I will write the old mean is 14,000, but the new mean is 1,200 divided by the square root, so it should be 200. I want to see your work, see that you end up with 200. And the answer turns out to be probability L bar greater than 15,000. Well, now I've got a bigger sample, so I've pulled that probability in even more. So that 15,000 that's out here, in terms of standard deviations, it's farther away from the 14,000 than ever before. So I expect it to have a small tail probability associated with it. And yeah, if you work this through, you should get most tables will say 0.0001, and that's because your z-score here, when you compute it into a z-score, you're going to be like, I think it's greater than 5, right? It's 5 z-score, 5 standard deviations out there, and that's a minuscule tail probability. It's actually a lot smaller than that, but the tables stop there. Most tables do. All right, looks like I've run out of room, so I'm going to have to rub something out. I was hoping I wouldn't have to, but read the next one and think about it. What we're going to do now is we're going to take 25 of these bulbs, and we're going to use one until it burns out, and we're going to unscrew it and put in the next one and use it till it burns out. We're going to unscrew it and put in the next one until it burns out. So we're going to burn them out sequentially. All right? And the question is asking, if we take 25 bulbs and do this, what is the cutoff length of time such that I can say that the probability is, how do I word it, is 90% that we will last at least that long. So can you give me a length of time such that I can say there's a 90% probability that putting those bulbs in one after another will last me at least that long? You know, when will I have to go back to the store, in other words? Okay, so have you read that and thought about it? I hope you can see that what we want is we want the total. We want this lifetime, then this lifetime, then this lifetime, et cetera, and add them all up. And what we want to do is come up with a number such that the probability is 90% that some of those lifetimes will be greater than that number. Can you see that the key really is going to be, excuse me, to figure out this problem for the sample mean? If I can figure out a value such that the probability is 90% that the sample mean will be bigger than or equal to that value, then all I have to do is to figure the total values and take that sample mean and multiply it by 25, right? Because there were 25 of them. Because how do I get the total length of all the lifetimes, or how do I get the sample mean? I take the total length of all of them, add them together, and divide by 25. That's how I compute a sample mean if the sample size is 25. So all I need to do is figure out what's the kind of the cutoff value such that I can say the probability is 90% that my sample mean will be bigger than or equal to that value. And once I get that answer, I'll multiply by 25 to get what I'm looking for. So what we say here in number 4, we have that L bar is normally distributed with mean. If you were confused about that one and now you think you know it, you should pause me and work it through. All right, it's normal with mean 14,000 and standard deviation 1,200 over the square root of 25, and that's 14,000, 1,200 over 5, it gives me a standard deviation of 240. And as I start writing in front of my face with pink, it gets hard to see, so I'm going to switch to blue. All right, so what we want is let's solve this for L bar. So first, let's solve this. I want the probability that L bar is bigger than or equal to some value. I want that to be 90%, right? 0.9. Okay. This is a problem we've done before. This is one where we're given the area and we want to find the corresponding data value, the corresponding random variable value, correct? And remember the way we do that, we've got to use z-scores. But we start by getting the z-score, and then we work backwards, all right? We've done several of these. You have to go back a few lectures, or yeah, just in your notes, and you should see what we do. But the first thing we do, excuse me, is, so first, we get the z-score. So I want the probability that z will be greater than something to be 0.9. So what do? I go into my table. Well, first off, I got a problem because it's greater than. My table only gives me probabilities for z less than a number, right? But I use complementarity to conclude that this is the same as I want the probability that z is less than something to be the complementary probability of that, which is 1 minus 0.9, which is 0.1. That's what I go look up in my table. And in the table, we find an area in, meaning deep inside. You got to go inside. The area is, I think it was 0.1003 was the closest. All right. So that gives us a z-score. If you back out of your table, we have a z-score of, what, that 0.1003, go out and up. You get z-score is a negative 1.28. All right, so Sorry about the squeaks. The probability that Z is greater than negative 1.28 is 0.9, or approximately 0.9, right? 0.8997 actually, but we're going to use that's our approximation. So what I need to do now is go backwards. And when I write it like this, you can see I'm going to convert it into a probability of L bar greater than or equal to, if you like. It doesn't matter, right? Whether we use greater than or equal to for a continuous random variable. But I'm trying to get back to there to find this number, right? So I'm going to just kind of undo what I would do if I were needing to find the z-score. And of course, you remember what we need to do there. The value we want, our cutoff, well, I won't use the word cutoff, I'll just say our desired L bar value, I get it by looking at the mean plus the z-score times the standard deviation for L bar. So standard deviation for L bar, and that is, so it's the mean L bar, and that is, the mean is, as before, always 14,000, plus the z-score is negative 1.28, and our standard deviation is 240, and that gives us, I get 13,692.8 hours. All right. So that is the value such that the probability that a single light bulb, the sample mean will be greater than that is 90%. To find the total, we multiply by 25. So multiply by 25, and you get, 342,320 hours. All right? So what we can say is, finally, so there is a 90% chance, 90% chance is a bad word, 90% probability that these 25 bulbs used in sequence will last greater than or equal to that much. So we'll just say it like this. They'll last at least 342,320 hours. All right. If you work that out, that's saying that's a little over 39 years. All right. So if you buy these 25 bulbs, use them sequentially, you got a 90% chance you won't have to go back to the store to get another bulb for around about 39 years. We'll stop.